Hello, this is Math Jazz from Almost Cool, and I have a live stream for you today. Today we're going to talk about some probability. So I'm going to talk a little bit about binomial probability distributions, and then I'm going to do some problems. So let's see. Here we go. So our first thing is we're going to define a binomial experiment, okay? So binomial experiment. There we go. So a binomial experiment is a finite it's a finite collection of trials. Each trial is binary. And by that I mean it either succeeds or fails. And succeed or fail is not necessarily succeed or fail in the English sense. We just have to assign one side as success and the other side as failure to determine, these are the two outcomes that are possible. Like flipping a coin, a head isn't necessarily a success in the English word sense of success, and tails isn't necessarily a fail in the English sense either. But we need to have a generic name for one outcome and a generic name for the other outcome, and success and failure are the two terms that have been picked for this. The third thing is that each trial is the same as all the other trials. That is, it has the same probability of success or failure in every trial. So if success's probability is 1 in 6 on one trial, it's 1 in 6 for all of the trials. I guess has the same probability for success. And the last one is each trial is independent of the others. Okay, so with this, we define, we've defined a binomial experiment. We are now going to give a formula for determining results of binary experiments. So, if P is the probability of success in a single trial, mind that 3 says that being success for a trial means it's the same probability of success for all trials. So So this is the probability of success in any one of the trials. All the trials have the same probability of success. And n is the number of trials then readjust my desk. Okay. Then probability of x successes is n choose x times p to the x times 1 minus p to the n minus x. I'm not going to prove this, but I'll talk through the pieces of this, okay? So the first thing is the probability of x successes. Well, if the probability of one success is p, then the probability of x successes in a row is p to the x. If the probability of a success is p, then 1 minus p is the probability of failure. Because if you don't succeed, then you fail. That's how the binomial experiments have to be, is that the outcome of a trial is either succeed or fail. You can say do or do not. There is no try. Okay, so if p is the probability of a success in one trial, 1 minus p is the probability of failing in one trial. Well, if there are n total trials and x of them are successes, then n minus x is the number of failures. So the probability of a failure and the exponent is the number of failures. So if we ignore this chunk of our equation, this is the probability of getting exactly x successes in a row times the probability of getting n minus x failures in a row. But that's the same probability as getting x minus 1 successes, then 1 failure, then 1 success, and then n minus x minus 1 failures. Basically, the probability of getting all of your successes and then all of your failures is equal to the probability of getting the same number of successes and the same number of failures in a particular order. Not in any order, but in a particular other order. So maybe we need to bring out the colored markers to demonstrate this. So what I mean is the probability of getting all of your successes, which I will write in black. So probability of getting all of your successes in order, and then all of your failures in order, is the same as getting the same number of successes. So 1, 2, 3, 4, 5, same successes. And the same number of failures. The probability of getting success, 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 fail, fail, fail is the same as going success, success, fail, success, 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 fail, fail. So I'm not saying that the probability of getting them in this order is the same as getting them in any order, but it is true that it's the same as getting them in any particular order. So let me write another one, like success, fail, success, fail, fail, success, success, success. So the probability of getting them in this order is the same as the probability of getting them in that order, which is the same as getting them in the other order. Any one of these orders is just as likely as any other one of these orders. So what we need to do is we need to figure out how many ways can we order our successes and our failures. Well, this many ways. So that is why we have this C and choose X. Because this is the probability of getting them this way. And then we need to add in the probability of getting them this way, and every other possible order that they could come. And the number of ways that they can be ordered is this. So we have our probability here, and then we find it again and again and again, and we add up all of those probabilities and all of the ways that they can be found, all of the different ways to order, in this case, 8 elements where 5 of them are successes and 3 of them are failures. And that gives us the probability of X successes in any order. Okay, so that was the formula that we're going to use and the way that we're going to use it. And let us come up with some problems to test this on. So we're going to say that we have a family of 5 children. So a family Okay, now each child can be either a boy or a girl. Okay, each child is either male or female. We want the probability of having 4 girls. Well, we have to decide whether a boy or a girl is a success. It really doesn't matter which one we choose, but in this case, we're counting girls, so we're going to say girl is success, because it's usually easier to have what you're counting be the success in your probability formulation, and what you're not counting is your failure. So we're going to say girl equals success here. So the probability of girl in one trial is equal to 1/2. And that means that 1 minus our probability of success is equal to 1/2 as well. So the probability of 4 girls is equal to 5 kids choose 4 times 1/2 to the, there are 4 girls, times 1/2 to the, there's going to be 1 boy. And we write that as, well, 5 choose 4 is 5 factorial over 1 factorial times 4 factorial, which is going to be 5. And then 1/2 to the 4th is going to be 1 over 16. And 1/2 to the 1 is 1/2, which is going to equal 5 out of 32. So 5 out of 32 is the probability of getting 4 girls. Okay, well, so the thing about this question is that the probability of success equals the probability of failure. And what we want, well, I mean, you want your probability of success to represent whatever problem you're trying to model, whatever situation you're trying to handle. But what we'd like to see now, I should say, is an example where the probability of success is different from that of failure. So let's say we want to know the probability of, let's say, rolling um, let's roll a 6-sided die 5 times and count the probability of rolling 4 ones. Okay, probability of rolling 4 ones out of 5 rolls. So, the probability of rolling a 1 on a 6-sided die is 1 in 6, which means the probability of not rolling a 1 or getting a fail is equal to 5/6. We're going to be rolling, so here's the probability of 4 ones. The probability of rolling 4 ones is going to be 5 choose 4 times we want to have success 4 times, and we're allowed to have 1 failure. In fact, the way this probability is being written is that we must have 1 failure, because we're taking the probability of getting exactly 4 ones and 1 thing that isn't a 1. So, with that, we can now simplify out our problem. So, 5 factorial over 5 minus 1 factorial is 1 factorial times 4 factorial. Well, that's just equal to 5. So, that's our 5. And then we want 1 over 6 to the 4th. Well, 1 over 6 to the 4th, we go 6 is 6 to the 1, 36 is 6 to the 2, 216 is 6 to the 3, and then 1,200 or 1,308, I think, is 6 to the 4. Let's check that. My powers of 6s might be weak right now. 6, 36, 6 times 6 is 36, times 6 again is 218, times 6 again is going to be, well, 6 times 2 is 1,200, 6 times 10 is 60, and 6 times 8 is 48, giving us a total of, well, 1,308, which may or may not have been what I said earlier. This is our 6 to the 4th, so we have 1 over 1,308. It's 1/6 to the 4th, and then we want times 5 over 6. Great. So when we multiply that out, we're going to get 25 on top, and we're going to get whatever 1,308 times 6 is, which I guess we can do here. 1,308 times 6 is going to be 6,000. Plus 1,800 plus 48, which is going to equal, I guess, 7,848. This here is the probability of rolling exactly 4 ones if you're rolling a die 5 times. Okay. So, let us do another problem. Oh, the first problem we should do is we've been handling only when we get exactly a certain number of die rolls or children or whatever. We've been calculating the probability of exactly X successes out of N trials. But maybe we want to know the probability of getting at least a certain amount of successes out of a certain number of trials. So let's redo the problem we just did, but instead of the probability of 4 ones, we're going to do the probability of at least 4 ones. Well, that's going to be equal to the probability of 4 ones plus the probability of 5 ones. I don't have a special formula that'll do this one easily, unfortunately, but it's not too bad to just use the formula twice. Now, we already calculated that the probability of 4 ones was going to be 25 over 7,848. So we can just write that one in. So we get 25 over 7,848 plus we have 5 choose 5 because in this case there are 5 successes that we need. So that's out of 5 rolls we get 5 successes. That's this. Times you need 1/6 to the 5th, which represents rolling a 1 5 times, times 1/6, which is 0. This here is 1, and so is this. So we get 1/6 to the 5th. Unfortunately, we know that 1/6 to the 5th is 7,848. So 25 plus 1 is 26. This is our probability of getting at least 4 ones out of 5 rolls. Okay, so these aren't so bad. We're just using the same hammer that we developed at the beginning of the video. You know, this binomial probability formula that we showed at the beginning. So that's not too bad actually. It's fairly it's just kind of plug and chug. But it does give us some tools to do some problems that would be fairly complicated to do with our normal permutations and combinations rules that we were talking about last week in the live streams. So it's an interesting little tool. Okay, so let's do some more problems. Let me pull some out of the book. So okay, actually, let's take a segue for a moment. And we'll talk about combinations and their relationship to Pascal's triangle. So, here is Pascal's triangle. You may have seen it before. We make 2 diagonal lines of 1s. One up to the right and one up to the left. And then we're going to make a diagonal lattice of numbers here, where every number is going to be equal to the sum of the number above it to the left and the number above it to the right. So this number here is going to be 2. Here's the first square of our lattice. It's on a diagonal, but you can see if we turned it, it would be a square. So 2 and 1 make 3. 2 and 1 also make 3 here. Next line is going to be 1, 4, 6. The next line is 1, 5, 10, 10, 5, 1. And while it looks pretty, you might think like, how is this math? instead of just kind of a design? Well, the answer to that is that this relates very closely to the combinations that we're using in our binomial experiment probability formula. So let's do something like this first. Let's have probability, well, not the probability, the combination. We have 0 items, and we choose 0 of them. How many ways are there to do that? There's 1. We have 1 item, and we take 0 of them. There's only 1 way to do that. If we have 1 item, and we take it, well, there's only 1 way to do that as well. If we have 2 items, and we take none of them, there's only 1 way to do that. But there are 2 ways to take 1 of the items, and there is 1 way to take both of the items. You should start seeing a pattern here. So it's 1 way to choose no elements out of 3. 3 ways to choose 1 element out of 3. 3 ways to leave 1 element behind out of 3. And 1 way to take all 3 elements out of 3. We notice we have this pattern, and it's going 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. And if we look at our triangle, those are the first 4 rows of Pascal's triangle. Now there's a way to prove that the values of Pascal's triangle are exactly the entries in, the values generated by combinations. We're not going to prove that in this live stream, but we might prove it in another video. But let's just feel, we'll test a high value, and by high I mean something that's still probably less than 10 items. And then we'll check Pascal's triangle and see if it's the same. So let's check, let's say, the 8th row and the 3rd item. So how many ways can we take 3 items out of 8? That's going to be 8 factorial over 8 minus 3 factorial times 3 factorial, which is equal to 8 times 7 times 6. Everything from 5 down cancels here with the 5 factorial, over 3 times 2 times 1. That's this 3 factorial here. Well, 3 and 2 cancel with 6. So this leaves us with 56. So 8 choose 3 is 56. Now let's go to our little tiny Pascal Christmas tree and continue it until we get to the 8th row. Notice that this is the 0 row, and then this is the 1st row. Just like this is the 0 column. They're on diagonals. The columns are on diagonals, but that's fine. This is the 1st. This is the 2nd. This is the 3rd. So what I want, if I go 0, 1, 2, 3, 4, 5, we want to go 6, 7, 8. This entry is 6, this one is 7, this one is 8. That actually works for all of the rows. The 1st entry. So this is the 0th entry, it's the line of 1s. And then the 1st entry is this line here. It just counts up, because every time we go down, we just add another 1 to what we had, and it just counts up which row you're on. So this is the first row, the second row, the third row, the fourth row. Again, the top is the 0 row, so it looks weird pointing to this thing and saying, well, this is the first thing in the row and this is the 0th thing, but it makes sense when you're counting it this way for Pascal's triangle. Anyway, so we get down to the 8th row. We want the 8th row, which means we have to compute 5 plus 10 is 15. 6 plus 15 is 21. And we need to calculate 10 plus 10 is 20. And 15 plus 20 is 35. And 21 plus 35 is 56. Notice that the 0, 1, we didn't calculate 2. 3, this element is equal to, in fact, 8, choose 3, as we predicted. And if you were feeling that you wanted to complete this, if you're a completionist, this might be 28. 7 plus 21 is 28. We have 15, 6, 1, 35, 21, 7, 1, and 1, 8, 28, 56, and this part here in the middle would have been 75 if I hadn't covered that up with a 8 choose 3. Anyway, this is our live stream for today. Tomorrow we're going to do more probability, and we're going to continue to build up new tools so that we can approach new and interesting problems. Please catch us tomorrow as we do more probability problems. I hope you're enjoying learning some math and some probability. Have a great day. Bye.